Howdy, howdy. Welcome back. Today we're going to be looking at the enumerable type, which is going to allow us to create a variable that has multiple variants. We're going to look at pattern matching using if-let and then also match. And we're going to be using pattern matching mainly to do different operations based on the different kinds of values that a variable might be. We're finally going to then introduce the option enumerable type. And these are all pretty essential components of the language to help us better understand what's going on in the random number guessing game that I'm thinking we're going to get into in the next video. We're also going to spend approximately 3 seconds on while loops. If you want to do while true, it's literally loop. That's the same thing as writing while true. Just a little fun factoid for you. Okay, pretty simple. Moving on to the meat of this, we're going to go into enumerables. Like most other languages, an enumerable lets us define multiple types that a variable can be. Unlike some other programming languages, Rust absolutely loves these, and you'll find yourself using them a good bit. For example, let's make a deck of cards, right? A deck of cards, we have a suit of cards, right? And that suit could either be a heart, could be a spade, could be a diamond, or it could be a club. Now, in a deck of playing cards, we have the cards themselves, a suited card, right? But we also have blank cards at the top sometimes, and we also have jokers in there, right? So I'll make another enum called card, and this is for any card in a deck of cards. And in our deck of cards, we can have a playing card, which we'll get to in a second. But we can also have a joker, and we can also have a blank card. Now, a playing card by itself is not really useful information to us. We can go ahead and actually pass in some values that a playing card can hold. In this case, we want the playing card to hold a suit, and then also an unsigned 8-bit integer for the value that the card can hold, like ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get the idea. By convention, we use uppercase camel to define the enum and also the variant. To assign a variable to an enum variant, we can go ahead and use our handy dandy let. Let's do the Queen of Hearts, because that's your best bet, right? Ha. I'm so funny. So our Queen of Hearts is going to be a card. What kind of card is it? It's going to be a playing card, and that playing card needs a suit. What kind of suit? And we use double colon to access our variants, right? So it's going to be a suit, that's going to be a heart, and the queen would be 12 in this case. We can also do the 2 of clubs just to nail down the point here. Pause the video real quick and think of how you would write the 2 of clubs. I mean, pretty easy pattern to follow. And again, this double colon syntax in order to access the variant on the enumerable type. But what if we want to name our values passed into an enumerable variant? I'm going to create a third enum type down here called shape. And I'm going to give it the variants circle, triangle, rectangle. Feel like I'm in 3rd grade, but yes. And we want these to hold values, right? Except it might be a little confusing to just have unnamed values just floating around in here. They'll be accessed in the same order as we did down here, but we might want to name them. In order to name them, we could do curly brackets, and this is kind of like defining a dictionary if you're coming from another language or a struct. So we want this to have a radius of u8. A triangle can have a base of u8 and a height of u8. And then a rectangle will have a width of u8 and a height or a length of u8. Okay, great. We defined a couple variables that are enumerable types, or should I say variants of enumerables. But what if we want to do operations based on these variables that we just created? Like, how do we figure out that there's a 2 in this 2 of clubs? First of all, we need to check that it's equal to the variant that we're trying to extract the value out of, because this could be a joker or a blank which doesn't have a value in it. We need to first make sure that it's a playing card. And in order to make sure that it's a playing card and get the information out of the playing card, we do an if-let syntax doodad here. So I'll go ahead and say if-let card, playing card, suit value is equal to our queen of hearts. Then we can get out the suit and the value. This is basically just matching. Oh, what did I do here? Oh yeah, we'll get into this later, but I basically did not implement the display type on suit. So we're just concerned with the value right now. I just wanted to come back and say real quick that since we aren't really using suit, by convention, we underscore unused variables. And we get rid of our little warning here. So this is a form of pattern matching. We're basically saying, okay, is the Queen of Hearts a playing card? And if so, let's destructure the suit and the value out of it. But we're, again, more concerned about the value here. And we can do whatever we want with this value. We can do value +5 if we ever wanted to do that. But more often than not, we're usually concerned about all the variants that an enum variable can be rather than a single one like we did right here. For example, if we wanted to write an area function for our shape, we want to do it for circle, triangle, and rectangle. But we might not exactly know if we're getting a circle, triangle, or a rectangle. That's where the match expression comes into play. You can think of the match expression as a pretty clever way to write something like this for everything. So it would be like else, let, if, let, card, joker equals Queen of Hearts. If our Queen of Hearts is a joker, which it isn't, then we could print out it's a joker, etc. for everything. But that gets a little cumbersome. I'll first show you the match expression by writing an area function for our shape enumerable here. So I'll go ahead, create an area function that takes in a shape, which is a kind of shape, and we're going to return a float. Now we're going to do a match, M-A-T-C-H, on shape. And now we basically cover every possible value that shape can be. As you can see here, we get a little hint from my IDE, circle, triangle, and rectangle. So if it's a circle, and again, double colon, and again, like the if-let, we're extracting the value. So in the case that it is a circle, we get the radius. And just for brevity's sake, in order to actually get the area out, I'm going to do a quick constant here. So our radius, or should I say our area, is going to be equal to pi times radius squared. For our rectangle, I'll do triangle next just to stay in the same order. It's going to be 0.5 times base times height, comma, because we're going to a new pattern matching expression, or new pattern matching. This part is an expression. The whole thing here is part of your match block. So I'll do shape, rectangle, width and height, length I should say. It's going to be equal to our width and length, except we want this to be floating point, and right now this is an integer. See, it's going to get mad at me. So we're going to go ahead and I'm going to cast these all to floats real quick. Okay, so this is how we properly cast everything. And do note again that we need to cover all the possible values a variable may be. Otherwise, our program's not going to compile. So if we comment out our rectangle here, as you can see, editor's already complaining, but I'll do a cargo check anyways. As you see, we have an error here, shape rectangle not covered. Okay, next we're gonna write a function that's gonna print out the value that a card might hold. For example, for any suit of card, we're gonna print out ace if the value is 1, the number itself if it's between 2 and 10, and then jack, queen, king for values 11, 12, and 13 respectively. I'll create the boilerplate for this function. I'll call it get card string, and it's going to take in a card, and we're going to return, in this case we haven't gone over ownership yet of strings, so we're going to just print ln. So we're not going to return anything, but I encourage you to pause the video and think of how we would do this. And again, to print out the card string, we would do print ln. So if you want to go ahead and pause the video and think about how we would do that with match statements, go ahead and try that real quick. Okay, so we would first need to determine if our card is a suited card, and then match the possible number values a suited card might hold to its appropriate string. So we're going to use a match expression for both of these cases. So first we're going to match card, and if the card is a playing card and we want to get the suit and the value out of it, we're then going to, we can do brackets when we're doing a multi-line match statement, or match expression, match block here. So we're going to also match the value of the playing card. For when it is 1, we're going to print out ace. When it's between 2 and 10, we can use this inclusive range operator. So 2 up till 10, that's saying 2 through 10 inclusive. We can do print line, and then we just want to do the literal value. And in order to do so, we use the string formatting, the string format with brackets inside of a double quotes. And let me fix this real quick as well. When it's equal to 11, want to print out jack. 12, print out queen, and then king for 13. Now next we're going to create a match expression for the Joker card variant and simply return Joker. So if our card is not a playing card, it can be a Joker. And we just want to print out Joker. And we'll do the same for a blank card. Alright, so let's check our progress real quick with cargo check. Pause the video real quick and see if you can guess what's going to happen. Although the IDE might have given us a little bit of a guess here. So I'll go ahead and do cargo check, just check our progress. What's this? A compilation error? Where did we go wrong? As you can see, we didn't cover the cases where value is 0 or 14 and greater. See, this match expression is really useful because at compilation time, it's going to check to make sure that we're covering every single branch of possible code. In this case, we're not covering when it's 0 or 14. So I'll go ahead and implement that real quick. Now, if a card is 0 or greater than 13, that's not really a valid card number. So we're just going to go ahead and use our wild card here. Underscore is a wild card. So that means match anything that hasn't been matched before. And we're going to print out invalid card. So sad. We're going to get into error handling later. I'm again going to add that we should underscore unused variables, and that's going to help our cargo check. So if I do cargo check again, we should see we don't get any errors related to an unused variable when it comes to this suit variable. Okay, let's do cargo check again and see what happens. Alright, so we just get warnings at this point just because we're not using our get card string function at this point. Let's go ahead and use it. So I'll go ahead and get card string Queen of Hearts, 2 of Clubs. Let's see what happens. What did I do wrong? Ah, yes. Yes. We haven't got into ownership yet, so I'm just gonna comment that out. And we'll explain this later, why that did not work, but I'm just gonna keep it to match statements for now. So as you can see, we have a queen and a 2 that we printed out. We first matched the card against the playing card, and then if it is a playing card, we saw that if it's a numerical value 12, we print out queen. If it's between 2 and 10, we print out the value itself. And just to nail the point, I'll do the same if we got a card that is a playing card with or not a playing card, just do a joker. We should get a joker. As you can see, we matched this branch right here. Alrighty, so now that you know the basics of enums, their variants, and match expressions, I'm going to introduce a cornerstone enumerable that comes baked into the Rust prelude. And again, the prelude is a set of macros and other definitions that we use very commonly throughout development. The enumerable type that we're going to introduce is called option. I'll write out some pseudocode that defines this option type. It is more or less this. Ignore this for now, but that is literally it. Option is used when our function might return a value or might return nothing at all. None can be thought of as a null in other languages, except it's actually pointing to something called none instead of pointing to literally nothing. So we're going to have something or nothing. We're going to optionally return a return value or nothing. And don't worry if this bracket T syntax is a little bit confusing. We're going to go over generics later, but that's basically saying if we give this option some type, it's going to return some type. We'll go over it later, and it's going to make more sense eventually. So I'm going to define yet another enumerable type down here, and we're going to call it coin. And that can have a value of either penny, nickel, dime, quarter. We're also going to create a function called getCoin, which is going to return the variant, so penny, nickel, dime, quarter, based on the integer that we pass in. So 1 should equal penny, 5 should equal nickel, 10 should equal dime, 25 should equal quarter. Again, if you want to pause the video and think this through real quick, please feel free. So I'm going to go down to the bottom of our main function and create our get coin variant function, and we're going to take in a input denomination, and that's going to be a unsigned 8-bit integer because we don't need anything bigger than 255 in this case. So we're going to again match, and we're going to match our input denomination. If it is 1, we're going to return, in this case, I should add that up here, skinny arrow, and we're going to return a coin. Actually, we're going to return an option of type coin. So that's where that T kind of comes up. Oh, I deleted our example here, but we're basically saying we're going to return an option of type coin. So if it's 1, we're going to return some coin equals penny, or a coin of type penny. 5 is going to be some coin nickel, some coin dime. 25 is going to be some coin quarter. And then in the case that we don't match any of these values, we're going to return none. And again, this is an enumerable type, or enumerable variant, I should say, that does not hold any value. This is also an enumerable variant from the option enumerable that holds a value, quarter. And because we don't have a semicolon at the end of this match expression, we're returning the possible branches that we hit. And we have covered everything. We've covered 1, 5, 15, or 1, 5, 10, 25, and then anything that is not one of those values. I'll just add really quick, just to make sure it's not confusing at all, that we're basically exposing these variants in the prelude. As you can see, it's of type option, and it is a variant of some T. If we wanted to be explicit about it, we could write something like this. This is saying the same thing without the option enumerable beforehand and specifying the variant. It's just shorter to write it without option because we're already exposing it within the prelude. Okay, great. We got our coin variant function. Let's try using it now. I'll go back up to our main function, and I'll say let maybe a coin equals get coin denomination, variant I should say, with the denomination of 25. Our maybe a coin variable could hold a value, but it could also be none. So it could either be an option, well, it is an option, and our option will be either some coin or none. Think about how you might get the value of coin if there is indeed a coin in here. We have a couple of options. Our first is a match. We can match maybe a coin. We could do, if it's some coin, we could just get the coin. And this is the cool thing about match expressions, is that we can assign this to a variable. And we're just shadowing coin in this case. Or if it's none, we can do something before we even assign coin. We could just return from the main function, and this is completely valid Rust. So instead of assigning coin to coin, if it's none, before we even assign it anything, we're going to return. We can also do some transformation. We can say print oh no, and then return if we want to. Or we could do a default coin, like dime. The other option we have is using our if let syntax. If let some coin equals to maybe a coin, then we can do some operation on coin. We have coin available in this scope, else we could return early from our assignment here. Or should I say we just return from the main function right here. Our third option that we haven't gone through is the let else syntax. And this is a shorthand form that is especially useful for when dealing with option enumerables. So I'll say let some coin equals to maybe a coin. Otherwise, we can just return. And now we have exposed this coin variable to our main function. So now we can use coin here, and we can do something like print coin. That is, if coin has the display trait, which it doesn't have at this point, but we can do some sort of operation on coin here. We can do get the next higher coin variant, or whatever we want to do with coin down here. It's just an easy way to unwrap the value of coin, or if something goes wrong, we can return early from our function. And that's a wrap for this video. In summary, we went over enumerables. We also went over pattern matching with let else, if let, and then also the match expression. And we also covered the option enumerable type. And that's basically this video. The next video, we're going to go over the guessing game. Finally, get to something meaty.